Hey guys, this is a continuation of our topic on shear flow and shear center. So I'll be discussing to you now a problem to present or to demonstrate the uh, procedure on how to get the shear center and also the graph of the maximum shear stress and its location. Okay, so for the problem shown, we have an angle bar with the dimensional properties as given. This is actually an angle bar with equal legs, since your leg 1 and leg 2 are of the same length. So this is an equal angle with a thickness of 5 millimeters. So the units are in millimeters. So let's take a look at the orientation of the angle bar with the x and y axis passing a centroid. So these are now the principal axis of the shape or the section. And we assume that the centroid of the section is referred to the corner, no, as your origin. So this is your origin for the value of x bar and y bar. Okay, so for the location of the centroid of the angle bar, since this is not a standard angle, we cannot go into the table to get the centroid of the section. We simply apply the Varignon's theorem for the area concerned using the simple formula A x bar is simply equal to the summation of individual areas times x, and area y bar is simply equal to the summation of area times y. Okay, so this refers to your Varignon's theorem. So for y bar, this is now your summation of area y, and for your x bar, so this is simply the summation of area x. Taking a look at the on how the elements are defined, so I just cut this into two areas. So this is now my first area 1, and this is my second area 2. So I have now two elements. The area of 1 is simply equal to the length multiplied by the thickness, 300, and the area of 2 is simply the length minus the thickness multiplied by the thickness, which is 275. So we can verify this very well on this figure, which is actually okay, this part here, area 2, and this part here, which is area 1. Okay. Now for the individual centroids, we have to redraw, of course, in order for you to be able to distinguish the centroid. If we redraw the angle, which is divided into two areas. So for your x bar or x's, we have here L1 over 2 and T over 2, okay, as your individual area, lever arms, okay. So this is equivalent to your x1 and this is equivalent to your x2, such that your equation here has simply L1 over 2 and T over 2 as your x1 and x2. Okay? While for your y bars, if you will look into the distances y2 and y1, so I have here my centroid. So for y2, I have here t over 2, or sorry, for y1 and for y2, I have here L2 minus t over 2 plus t. Okay, so these are now my y1 and this is my y2. Okay, for the moment of inertia, so my y bar and x bar, since this is symmetrical, will actually be the same, no? Same value, and this is in millimeter. So for your moment of inertia, so this moment of inertia, your Ix and Iy follows the formula which is equivalent to Ig plus summation, summation Igx plus A dx squared, and for y we have the Igy plus area dy squared. Okay, so for your Igx, we have two components of your Igx. We have the first component, or sorry, the first component is this one, okay, and the second component is this one. Okay, so this is now my Ig1 x, okay, is simply equivalent to L1 T1 or T cubed over 12, and my Ig2x is simply equal to E times L minus T cubed over 12. Okay, so for my Igy 1 and 2, okay, so I have here now my Ig2y. So this is simply equal to, okay, on the y-axis, this must be L minus T times T cubed over, this is L2 rather, okay, this is L1. Of course, L1 and L2 are just the same, so no worries about it. In case they are not the same, so you have to be very specific. Over 12, and this is Ig2 or 1 IG1Y is TL1 cube over 12. Okay, so this is the one that you will be plugging inside this equation for your Ix and Iy. Okay, so this is of course your IG1X, this is your IG2X, this is your IG1Y, and this is your IG2Y. Okay, and for your A dx squared and a dy squared, so we just take a look at the centroid here. The distance from the centroid of the element to the centroid of the bar. So if I have here my x centroid, okay, so this is the centroid of the whole section. The distance from here to here is my d1x, and the distance from here to here, sorry, here to here is my d2x. Okay, so for my y direction, dy direction distances, so I have here my centroid, I have my centroid here, so this is my dy1 or d1y, and for my distance here, I have here my d2y or dy2. Okay, so these values here are actually summarized here. So this is my dx1, dx2, and this, or d2x, d1x, and these are my dy1 or d1y and d2y. Okay, so they are complete. And normally, since it's symmetrical, your check is actually by simply looking at the values, they must be the same. Okay, and for the product of inertia, this is just an additional exercise for you. No? The product of inertia is simply equivalent to summation a dx dy. Okay, so this is my a1 is my d1x d1y, and this is my d2x d2y. Okay, so I have two elements, I have two products, and I get 1.184 10 to the fifth. These are all in millimeters to the fourth. Okay, millimeters to the fourth, millimeters to the fourth, millimeters to the fourth. And finally, for your XO and YO, I simply subtract X bar minus T over 2, 14.348, and my YO is simply Y bar minus T over 2, 14.348. They are just the same. Okay, so this will be the location of your shear center from the center of gravity. Okay, so if you want me to have a drawing on it, so this is simply the distance from the shear center to the centroid, simply your XO and your Y. Okay, so this is the center of gravity and this is the shear center. Okay, so that's it for the first four requirement. We have solved now your centroid, moment of inertia, product of inertia, and shear center. So we will be solving number 5 on the next video. So thank you for listening.